All right, our last set of notes for Unit 2 is going to be taken from Section 3-4, which has to do with perpendicular lines. We're going to be looking at a couple of definitions and at some theorems that come from everything else we've talked about so far in this class. We're going to be looking at specific implications of the parallel line theorems and some implications of their converses. Before we get too far down the line, though, we need to talk about the term perpendicular bisector. When we talk about perpendicular bisector, we're looking at a specific line or segment that intersects another one at a right angle and through the midpoint. So let's get some of those highlights written down. First of all, it has to include the midpoint. It also has to hit at a right angle or be perpendicular. So let me draw an example of this. Oh, and I guess we should also write down the reminder that when we talk about perpendicular, we're talking about that right angle. Okay, so remember that. Now, let me go ahead and let's draw a segment here. There's my happy little segment. If I want to talk about the perpendicular bisector of that segment, that means I'm looking at something that passes through its midpoint. So it cuts it in half. Then, in addition, it's going to do it in a way that passes through. That's not what I wanted. That's what I wanted. Passes through at a right angle. Let's clean it up just a pinch. There we go. So this is going to be perpendicular. Now slap some labels on here, A, B, C, and D. I could write that AB is perpendicular to segment CD. That's part of it being a perpendicular bisector. Not too bad translation. I can only bisect segments. I can never bisect lines because lines go on forever. So only segments can be cut in half. So it's important to note that this point right here is the midpoint. So again, and if you look at the term perpendicular bisector and break it down, perpendicular, we know that refers to something that is going to hit at a right angle, perpendicular. And then when I talk about bisector, remember bisecting something, bi is to, and sect is to cut. So a bisector cuts into two equal parts. We've already talked about segment and angle bisectors earlier in the course. So we're kind of throwing these all together into one concept now, which is the perpendicular bisector. Now, when we start to look at some of the theorems that come out of these parallel line postulates and theorems, we're going to focus today just on ones that involve right angles. So here I'm going to take two parallel lines. So there are those. Now I'm going to draw a transversal. Now the transversal will be a little bit unique because it's going to be perpendicular to one of those two lines. Now again, we said these lines are going to be perpendicular, so they're parallel. So there are my arrows to show parallel. Now I'm going to add on the fact that this is perpendicular. So what I might write for this, I might say, let's put some labels on here. Here's L, here's M, there's T. I might say that if L is parallel to M and T is perpendicular to L, then it's going to follow, then I can say that T is perpendicular to M. Now think about what we've talked about in this class before. For example, if I were to say, what's this angle here? I'll call it angle 1. We know angle 1 is 90 degrees. Angle 2, down here, is a corresponding angle. They're both in the upper right position. So since they're corresponding angles, I know they're going to be congruent. That comes from the fact that the lines were parallel. Parallel lines make corresponding angles congruent. That's the corresponding angles postulate. So it more or less follows then that if I'm talking about given this perpendicular here, I know this is also going to have to be perpendicular using the corresponding angles postulate. I know that if this is 90 degrees, that it's only logical then by that postulate we've talked about, that that's also 90 degrees. There's another implication that I can talk about, which is let's take a fresh page and draw 2 more lines on. Now this time, I don't know that the lines are going to be perpendicular or parallel. I don't know that I have parallel lines here, so I'm not going to mark them as such. There's my transversal. But I do know, and let's talk about, there's L, there's M, there's T for the transversal. This time coming in, I know both of those are perpendicular. Think about what we've talked about. Those are corresponding angles that are 90 degrees. If the corresponding angles are 90 degrees, it would follow then that these lines must be parallel. Think about the converse of corresponding angles. The converse of corresponding angles is the postulate that tells us if the corresponding angles are congruent, then the lines are parallel. In this particular example, I'm saying, however, that if L is perpendicular to T and M is perpendicular to T, then, and now I'm looking for a consequence. Well, I've got the corresponding angles are congruent. That comes from them both being 90 degrees. It makes sense then that I can say that these lines are going to be parallel. That would be a logical consequence. And so again, this is a theorem that I can then quote. If, and now instead of saying this in this form, perhaps I might say, if a line is perpendicular to 2 lines, then the lines are parallel. Now, this particular theorem doesn't have a name. However, this one technically does. It's called the perpendicular transversal theorem. As a general rule, I'm not overly worried about the names of these particular theorems as much as being able to prove them later as part of your exercises. There's one more I want to touch base on, but I think it's almost too easy to say. And that is the last of the theorems that this section provides for us. It basically says this. Let's say you have a line. So there's a line. On that line, I'm going to go ahead, I'm going to drop a ray. Okay, we'll go this way with it. And that ray comes in such a way that these angles are congruent. So there's L, there's M. And what we're going to say is that if angle 1 is congruent to angle 2, then L is perpendicular to M. Now think about this proof for a moment. I'm showing you here, I've got a straight line. I'm going to put a line on an array that divides this into 2 equal parts. Well, we know already that a complete angle is going to be 180 degrees. If I make these into 2 equal parts, so if I were to call that x and that x, since they're equal, I could do some math. X plus x is 180. Solve for x. 2x is 90. I'm sorry. 2x is 180, and therefore x is 90. That would imply then that those are each of these is 90 degrees, and that this conclusion follows. But by stating it as a theorem, I don't have to do the work of that proof every time I want to explain it. And that would be the last of these perpendicular theorems listed in 3.4. Now, there are a lot of theorems we point at and a lot of names we've talked about. For example, the perpendicular transversal theorem is one of the names we've thrown around. We've also thrown around all of the theorems that relate to how these angles with parallel lines are related. Part of your task for Monday is going to be starting to look through your notes and collect a list of the theorems that we've used in proofs or that we've talked about by name, as those are going to be the most important ones to know when we get to the end of the unit. The ones that don't have names, like this guy, be prepared to know what they mean. So if I hand you this implication, perpendicular lines, can you give me parallel lines? Or if I were to draw a fresh picture, if I were to sketch this for you, and then tell you as part of your work that I've got perpendicular here and perpendicular here, can you conclude these lines are parallel? You don't need to name what theorem, but can you conclude it? And lastly, can you prove it? As I discussed the theorem, I like to think I laid out most of the framework for how that theorem is going to flow. That's the kind of thing we're going to be translating into a formal 2-column proof as we wrap the unit up. All right, see you all on Monday. Hope you had a good homecoming.